Hi guys, this is our faculty KANNADASAN sir, and today we are going to do the program language translators. These are our friends, one is Akhil and one is Satvesta and I am is Manikanta. And first question, we are going to see the questions for the following grammar. The following grammar is A tends to A dollar B slash B, B tends to B slash C slash C, C tends to C at the rate D slash D, D tends to D. Now this is the past diagram for this grammar, for the given grammar. For C, A tends to A dollar B. Now A is converted to A dollar B. Now again B is converted to B slash C. Now from A is converted to B, right? B is converted to B slash C. From that we can see B slash C. And for this and C tends to C at the rate D, and so you can see that C stands to C at the rate D and D tends to D, and we can directly write D tends to D, and again C is connected to D from the above given expression. C tends to D and D is to D, and wherever C you can write a C to D, then D to D, and D to D, C to D, C to D, and this is the final parse tree of the given grammar. And now we have to see the precedence of the grammar. And dollar and is converted to a dollar B. Dollar has the highest precedence, thus it is at the root position. And now see for the hash. Hash is the precedence lower than of dollar and therefore is a part of the subtree. And what is meant by at the rate? At the rate is the lowest precedence and is there at the lowest part of the tree. Now by this we have completed the precedence of the grammar. Now we are going to do the construction of DFA by the given regular expression. The regular expression is a plus b whole star, abb plus a power plus b. Now by using the Thompson's rule, we are going to draw a diagram for the given regular expression. The given expression is first we will draw the diagram for the a plus b whole star. Now one is a start state. Now from the 1 we are going to connect to the 2 and 2 to 3, and while 1 to 2 is connected to epsilon and 2 to 3 is epsilon and 3 to 4 is A and 4 to 7 is Z and 5 to 6 is B and remaining are epsilon. So by this by this 7 is connected to 2 and 7 is connected to 2 and 8 is connected to 1. By this and a plus b whole star conversation is completed. Now we are going to do the second part, which is the abb plus a power plus b. Now 8 is converted to 9, it is epsilon. 9 is converted to 10, 10 is converted to 11. In the uppercase it has A, and 11 to 12 is B, and 12 to 13 is B, and 14 to 15 is A, and 15 to 16 is epsilon, and 16 to 17 is B, and finally it is 18 is our final state of the given diagram. Now we will connect both the diagrams and by the using the Thompson's rule. Now see, 1 is connected to 1, 2, 3, 5. How is connected 1, 2, 3, 5? 1, 2, 3 and 5. 1, 2, 3 and 5 till 1. For the 2 is 2, 3, 5, and for the 2 is 2, 3, 5, and 3 is for the same because there is no epsilon, so that we can't go further for it, and it becomes a. Now for the 5 also it is 5 only because there is no epsilon, so that it can't go further, and it is 5. And for the 4 is 4, 5, 7, 8, 9, 2, 3, 10, 14, 15. And for the 6 is 5, 6, 7, 2, 3, 8, 9, 10, 1, 15. Now for the 7 is 7, 2, 3, 5, 8, 9, 10, 14, 15. Now for the 8 is 8, 9, 10, 14, 15. Now for the 9 is 9 connected to 10, 14, 15. Now for the 10 is there is no epsilon, so that we can't go further, and is connected to only 10. Now for the same also 11 also is connected to B, right, so that there is no epsilon, we will write it as 11. For the same for the 12 and 14 and 16, for them we will write it as same. And now for the 14 is 14, 15, for 16 is 16, 17, 14, 15. Now for the 18 is 18, 19. 19. Now this is the diagram. This is the table for 1 is connected to A, and each of the element is connected to A and B. Now we will see the 1 is connected to A through which node? 1 is connected to A through 4, So we'll write it as a 4, and 1 is connected to B is through 6. So we'll write it as a 6, and 2 is connected to A is 4, and 2 is connected to B is 6, and 3 is connected to the A is B. And now we can see that 3 is there is no connection to the B. So that we will write it as a 5. For it as a 5. And now for the C, for the 4 is 4, 11, 16, and for the B is 6. For 5, C for the 5 to A is there is no connection, so it will remain as a 5. For the 5 to the B is connection is and 6, and for the 6 is 4, 11, 16, and B is 16, and 7 to A is 4, 11, 6, 16, and 7 to B is 6. Now 8 to A is 11, 16, and 8 to B is 5, and 9 to A is 11, 16, and 9 to B is 5, 10 to A is 11, 10 to B is 5. Now 11 to A is 5, and 11 to B is 12, and 12 to A. There is no connection to the A, so that it will written as a 5. For the same as till 13. And now for the 14 is connected to 16, and 14 to B is 5, and 15 to A is 16, and 15 to B is 5, and 16 to A is 16, and again 16 to B is 18. Till same we will write it as till 18. Now we will see the deterministic finite out with the table. For the one connected to the A is 4, 16, right? So now we will go to the 4. For 4 is connected to A is 4, 11, 16 from the above table. And for the 4 is connected to B is 6. Now we will see that what are the different elements in the 6 rather than the others. 1, 4. There is 6. So we'll write as 6. Now 6 is connected to A is 4, 11, 16 from the above table, and 4 is connected to B is only 6. And now see from the 3 rows we will see that which we didn't cover. This is the 4, 11, 16. So this is the so far we didn't cover. So we will write it as 4, 11, 16. And 4, 11, 16 to A is 4, 11, 16 is same. There is no change. For the B is 6, 12, 8. Now for the 6, 12, 8 connected to A is 4, 11, 16. And 6, 12, 18 is connected to B is 16, 13, 8. By using this table, we are going to draw a diagram for this. This is a diagram how it is connected to 1 to 4, 16, and 6, 12, 18, 13 is the final state. By this there is some modifications, and we will doing this it find the deterministic finite automatic. This is the final diagram for our given expression. Now we are going to see the third question. This is the role of the parser. In the compiler model, the parser obtains the string of the token from the lexical analyzer and verifies that the string can be generated by the grammar of the source language. Now the parser runs into any syntax error by the source language. This is the source program. Once the source program is moved into the lexical analyzer and is taken to the token, and it is going to the parser, and again it maybe go to the next token by back as it go to the lexical analyzer. By this it goes to the parser tree and the rest of the front end, and it is the intermediate representation, and symbol table is connected to both lexical analyzer and rest of the front end. This is the parser returns and the source language, nothing but a source language. There are 3 general types. One is parser for the diagram, universal parser methods such as the Young's algorithm and Yearly algorithm can parse any grammar. The method are too inefficient to use in production compiler. The method commonly used in the compilers are classified in either top-down parsing or the bottom-up parsing. Now, the top-down parsing build parser trees up to the top root to the bottom. Bottom-up parsing build parse from the leaves and work up to the root. In both cases, input of the parse is scanned from left to right, one symbol at the time. The output of the parser is some representation of the parser tree for the stream of the tokens. Now, there are number of tasks that might be conducted during the parser, such as the collection information about the various tokens into the simple table, performing type checking and other kinds of semantic analysis, then generating intermediate code. This is the syntax error handling. The planning the error handling right from the start can both simplify the structure of a compiler and improve its response on its error. The program can contain error at many different levels. One is the lexical, such as the misspelling an identifier, keyword or operator. Now for the syntax, such an arithmetic expression with the unbalanced parentheses, and the semantics such as no operator applied on the incompatible operand, and logical such as infinitely recursive call. The much of the Error detection and recovery in the compiler is centered as the syntax analysis phase. The one reason for this is that many errors are syntactic in nature are exposed when the stream of tokens coming from the lexical analyzer disobeys the grammatical rules defining the program language. Another is the precision of the modern parsing method. There are detect the presence of syntax errors in the program very efficiently. Now, the error handling the parser has some goals. What now we're going to see the what are the goals. It should the presence of the errors clear and accurately. It should recover from each error quickly enough to be able to detect the subsequent error. So it will find the errors very quickly. It should not significantly slow down the processing of the correct one. So now there should be no correction of this should be correct the programs. And error recovery strategies. There are many different general strategies that a parser can employ to recover from the syntactic error. One is panic mode, one is parse level, one is error production, one is global correction. First, we are going to see the panic mode. This is the user where the most parsing methods. One, discovering an error, the parser discarding input symbol one at a time until a designated set of synchronous tokens delimiters such as semicolon or and is found. The panic mode correction often skips a considerable amount of input without checking for additional errors. So it is very simple. Now we are going to see the parser level recovery. On discovering an error, the parser may perform local correction on the remaining input. It may replace a prefix of the remaining input by some string that allows the parser to continue. Example, local correction would be replace a comma by a semicolon. The deleting an extraneous semicolon or insert a missing semicolon. Its major drawbacks is the difficulty it has in copying with situations in which actual error has conducted before point of detection. Now see the error production. If an error production is used with a parcel, can generate appropriate error diagnostic to indicate the erroneous construct that has been recognized in the input. Now see the global correction. Given an incorrect input saying X and the grammar G, the algorithm will find a phrase tree for a related string Y, such that the number of insertions, deletions, and changes of the token required to transform X into Y is as small as possible. So we have completed. Thank you guys for our video.